chemistry in the AM. I'm going to do a little review of what we have seen and where we're going then. We talked about a naming system. We have branches, the methyl, ethyl, propyl groups, etc., numbering, etc. We've worked through some examples, and I've actually gotten you to start on that assignment. I'm not going to go explicitly over anything unless you want me to. Is there anything we need to go over? I'm asking. Okay, it seems to be going good on Friday when you worked on this. So, I want you to flip to this page. It says isomers. And we are here. Isomers, good. Okay, geometric isomers. We've used the word isomer before. Same chemical formula, but structurally, they're hitched up a little bit. What are geometric isomers then? This is a little more specific. It results from different arrangements of groups around a double bond. Now, I think you can see right away, that's why one would be labeled cis and one would be labeled trans. You see how this is 4 in a row with the butene. This is 4 in a row and it's butene. However, they're structurally different. You have to use something here. I'm going to just get the model kit, so I'm going to pause the video here recording. Okay, I've constructed each of these. And you can see, like I said before, these are 4 in a row. 1, 2, 3, 4. 1, 2, 3, 4, right? You can see there's definitely a difference, though, between the two. And they cannot overlap and twist it around so that they're actually the same chemical. Right? They're actually different. So, there's some prefixes you're familiar with. It's 512. For other things. Cis and trans. Okay? So cis, same. If you're aware of that. Hey. Cis and trans, you're aware of prefixes. So I think the chemistry won't be straight. Cis, same side though, is what we're saying. So this, you notice that the long chain is on the same side of the tall. This, opposites, right? We'll call this the trans. Now, both of them are butene. We do have to list, and this is the way we listed before. We didn't worry about this. Before, I would have said CH3, CH, double bond, CH, CH3. This, what I wrote in blue, this is how you cis or trans. But to name this is either one. It would definitely be but because of 4, and butene because of double bond, EN. And we have to say where it is, because butene could also have it on the first and second, between the first and second. That'd be 1 butene. This would be 2 butene. Both of them are 2 butene. If I number them, 1, 2, 3, 4. 1, 2, 3, 4. They're both 2 butene. That's the lowest possible number of them. We have to tell the difference between left 2 butene and the right 2 butene. Correct? So, what do we do? That's the cis, same side, trans. Okay. It makes sense. One that I wrote up in the middle, the blue structure, is ambiguous. It's neither cis nor trans. You can't tell. I have to be more specific. So, now when you see a double bond, you have to question, are they both on the same side? Is the chain going to the opposite side? Cis and trans. Okay. Any questions here? People catch on to this. Now, there's actually differences in the molecules, whether they're cis or trans. Have you guys heard of like trans fatty acids and stuff like this, structurally, as opposed to cis bonds and stuff? They pack differently, the chains, throws a kink in there. Okay. And let's just take a look at this cis and trans example with chlorides attached, chlorines attached. Now, I have a boiling point difference here. They're both the same mass. However, there has to be something that's making one higher boiling point than the other. It has to do with electronegativity. This has stronger intermolecular forces. It has dipole-dipole as well as London, compared to the trans, which only has the London forces. Therefore, it takes more energy to bring intermolecular forces in a cis molecule, which means a higher boiling point. Just draw this in here and see what we're talking about. I put chlorine so it's really obvious. Okay. Now, chlorine is more electronegative than carbon, closer to proof. On your diagram too, I'd like you to draw this in. From the carbon towards the chlorine. And you see that there's a diagonally down and a diagonally up. They kind of, it's a tug of war, it kind of cancels each other out, right? Whereas with the cis molecule, they're both down, so you have a net dipole. So this is what I was talking about. Cis having dipole interaction, polar molecule. It's going to be held together a little tighter because it has a slight positive end, a slight negative end to the charge. So it does make a difference in chemical reactions to what it does on systems. We'll leave it at that. So we're going to have to be able to name and draw these kinds of things. We will. Don't worry about the chlorine name. So, second. Let's name and draw the following and then give you some practice. So the first thing you need to do is come up with the longest chain and, if possible, include the double bond, if possible. So with this one, I see that there's 1, 2, 3, if I think of the chain as that one. There. But I could talk about a chain that goes, including the double bond, 1, 2, 3, and I'm going to use that chain. It's the most common. Methyl propane. Like as in, same. Yes, it is. There's no reason why I couldn't consider that. So, because you mentioned it, I'll actually circle that one. So I'm going to circle this chain. This is the one I'm naming. It could have been the top CH3. Perfect. Okay, but it doesn't change the name. I've already heard the name. It's a propene, so 3, the double bond. And propene does not require a number to tell me where the double bond is. It's always between the first and the second. You've got to look from right to left. Now, you have to say where the methyl group is, so 2 methyl there's no cis or trans possible in this case because there's only cis or trans if you have a CH kind of group on the opposite side of the double bond. Okay? Don't assume cis or trans must be used if you see a double bond. Yeah. So I think this next one is a little more obvious. It doesn't use cis or trans because there's nothing here or here with carbon. Okay? There's not cis, non-trans. I'm going to cross it out. So we're going to just call this what? 1, 2, 3, 4. 1. Good. I use small letters for the names, but if you had a capital B for butane, that's fine. It's not like elements where you must use proper large and small letters. You can see the low for cobalt. I think the chain here is pretty obvious. So I got 1, 2, 3, 4, 5, 6, 7 in a row. Heptane, right? Now, what number should I use for my heptane? Nope, not whatever I want. It is trans. So, okay, we'll start with that. We know it's trans because it's opposite side. Now, I'm trying to figure out what the best way to label my double bond is. If I go from here, 1, 2, 3, 4th carbon to 5th carbon. No. This way, 1, 2, 3. You go from right to left, you get a lower number. So we're going to go to 3. Okay. Yeah. And change color only just because this diagram runs into the other one. The chain is pretty obvious. It's same side, they're both on the bottom. They could both be on the top. This is a cis, and I'm going to number it from right to left, give it the smallest number on the double bond. So it's a cis, because it's the same side. 2 for the double bond. 1, 2, 3, 4, 5. Hence. Okay. Now, I did all this naming with you. I need to get you guys to try the drawing for the next 3. I'll leave you be. I'll let you guys do it. Try these 3. We'll take them up right away. I'll pause the video while you're trying. Trans 3 hex E. The machine's even stuff. Thank you. The hex is 6. Here's how I think about it. I like to draw the double bond first just to get my geometry, but you don't have to do it. But here's what I'm going to do. And I know my double bond is kind of trans, so it's going to go then hex. So I'm thinking 3 hexene. So this is disappearing. CC 1, 2, 3, 4, 5, 6. I'm thinking that. Now I'm doing this in disappearing. So I know that the H's are also trans to each other, right? So I'm going to kind of work backwards. I'm going to go CH2, CH3. So that's 1, 2. 1, 2, 3, 4. And now 5, 6 on the other side. Okay. Now, you could have shown that another way with the CH3 here, CH2, CH2, CH3 here, and then the H is here. That's the same thing. Still trans. It's across the ball. Just flipped upside down. Okay? So as long as you drew one or the other. Now for methyl, so there's an attachment on the fourth carbon, cis-2-hept. So I'm going to draw the double bond first. You don't have to do it this way. I just find it easier myself. So cis, same side. Do we want to work on the top or the bottom for the same side for the carbon? What do you mean by full side same? That's not what we're asked for, though. Okay. So you're talking a different question. It doesn't matter. To the top, okay. So I'm going to attach my H's here because it's cis. So I'll use the top for the heptene. It's 2-heptene. So it's 2-heptene. So I know that the first carbon has to be a CH3. I tend to go left to right. If you did bottom, it looks the same as upside. So now this is 1, 2, 3, 4. Ooh. I'm going to just leave something here, and it'll be 4. But I'm going to just fill in my H's after. 5, 6, 7. Now the reason why I'm doing this way, and I'll put my H's on is flip it out. Okay. Methyl group on the fourth carbon. So 1, 2, 3, 4. This is the fourth carbon, so I'm going to put my methyl group here. That means this carbon here has 1 attachment, 2 attachments. The third one we don't draw in, but it's connected to the next carbon. I only have space for 1 H. So I'm going to put the CH, then CH2, CH2, CH3. We've done this a few times. I know I was going to skip right into this, but I wanted to. Now, what's implied here is that every carbon is bonded to another carbon. So 1, 2, 3, and then the fourth one to the hydrogen. 1, 2, and then 2 hydrogens, etc. If you drew it the other way around, that's fine too. Like both on the bottom, that's fine. I don't want to misplace this so I'm file it away. Okay, back to this. This one doesn't have cis or trans, and it doesn't even have a double bond. I just thought I'd throw it in. Pentine. Triple bonds do not lead to geometric isomers because they're linear across the triple bond. I know it because of the YNE and not an ENE. Somebody once told me that the way they remembered it was ENE ending for double bond is like an E equal sign. A double bond looks like an equal sign. That works for you, that's fine. Why? Why not? I don't know. If you know the E, you know that then the Y is the other, I guess. I don't know. That's their memory system. Just sharing it with you. If you want to get complicated, go ahead. Just know it, though. I don't care how you know. So, I'm going to put 5 in a row, 5 carbons in a row. Okay. Now, 2 pentyne. So between the second and third carbon, triple bond. 4 methyl. 1, 2, 3, 4. I'm going to put the methyl group here. And then I'm going to figure out what the heck's left over. Now, I could do it the long way that we showed initially. I'll just do that right now. Just put the H's there. And I'll finish this, but I'll show you the abbreviated way. You can do either one. And you have a question. What is your question? The attachment? Yes. This is what I was going to bring up. Continue. I don't know. Yeah, I do see what you mean because now we said use the lowest number possible for attachments, substituents. However, when we have a double or a triple bond, use the lowest number for that. And then number the attachments out. I'm not going to try to fool you guys over. I won't get things that are superly long, complicated. Okay. Now, how to write this as an abbreviated molecule? I'm going to call this CH3, C triple bond C, CH. This is the more compact way. This is the way I type it out if it was on the test.
I knew this.
Why did I say that? I don't know. You love the person I can't give up.
That was my brain before.
It'll get into your brain. You'll start. Okay. I think so. Anything to add or question about this other than good. You're contrarian. Anything KK says, say the opposite. No, actually, KMK. Yeah. I knew it was your middle name. M, middle is my middle name. Okay. One more thing, and this is what Zach is beyond what we need to know. But good on. This is a model kit thing, and I want to pause. You guys will get model kits out. Okay? You do too. So isomers, optical isomers, not geometric. They're different arrangements of 4 different groups around the same carbon atom, as Zach mentioned. The center is carbon. I'm not worried about what XYZ is. They could be chains with carbons attached to them. It could be chlorines, it could be hydrogens, all kinds of things. They're 4 different things. So I'm going to stand up with one of my molecules. So I've constructed this one for B. And this is what we got to see. This one for A. Can you twist B around so that it is? How do you do it? Can you match A and B? Can you make, let's hold A the same always. Can you make B the exact same? Can you twist it around? Yep, it is the same molecule. Now, the trick is, though, can you tell that without doing the model? Let's think about it. So, first of all, A and B are the same. I'm going to write that down here. A. Everything will compare. Let's just say everything is the same as A, or else different than A, okay? This is the same as A. Okay? Now, what you got to do is, though, how could you visualize that model without building it and change B to look like A? Well, what I'm saying, without building the model, can you tell that those are the same? There's a few ways of doing it. I put W, the red, at the top every time. Here's why. If you have this held still, and I'll show you this, it doesn't do well on video. Okay, Z. You see how mine is like this? If I think of B as, and I just rotate the top, I keep the top the same, and I just rotate it like this, in my mind, I'm rotating it, and that's the same as B's structure, right? So what I'm saying, so that this shows up on video, is if I rotate this, oh, I didn't need to make a full circle. So I spin it around as W as the axis. You see that that turns into what A is. Now, let's make a prediction. Is C the same as A? Can you spin? I could either spin it 2 spots. Does it become the same? Let's build this. Well, I'm going to build it. I've got C in my hand right here. Green, because I'm colorblind, you guys got to check my work. Right? Is that, I'm using this as blue, right? This is A, correct? Yeah, I'm going to switch my hands. I am using C. Oh, you are so sweet and kind. Anyways, so look at this though. When I hold these together, they're mirror images of each other. There is no way that I could ever spin this around to be exactly the same over. So what I was showing is that you see, and I'm just going to ignore the middle here. This is the exact mirror image. Right, left, right, reverse. The mirror image is not the exact same. So C is different than A. There's no way you could spin it. And I find the easiest way to check is if it's a mirror image. Yeah. So, as long as it has 4 different attachments to the center carbon. The other things could involve carbons too. If you CH2, CH3, like an ethyl group, one could be a methyl group, and one could, you know. Like, okay. So then, A and B are the same, C is different. Let's check out D. And you guys tell me whether you want to build it with your model kit or whether you could just look at it and tell me. And you spin, the way I think of it is, to look like this, because W is at the top. Can you spin this around? No, because see, Z's already in the right spot. You have to switch too. Ah, crap. That's not going to work, is it? But you built it. Okay. I'm going to come with my A, my colorblind A. So we played around. This is different than A. Oh, it's okay to spend half an hour with developing our understanding. This is different than A, right? E is the same as A because if I did the old spin, it becomes, so it's the same. Same as A. Yes? It doesn't matter if it's clockwise. As long as it's as long as you can hold one thing and spin it. I think at the top is spinning. It doesn't have to be at the top. It could be any one of them. Okay, hang on. We'll stay to this and I'll get to specific questions, okay? So, which isomers are the same? We've labeled that. By the way, the ones that are different, D and C, are the same as each other as well. There's really only two possibilities. You'll notice a few things too. Some people think of it as, if it only takes switching two things to make it the same, that's what this is, for D and A, then it isn't, they're mirror images of each other. They are different. Okay? And you notice that in C, two things switched, then they'd be that, they're mirror images of each other. Okay? That's one way of thinking of it too. You don't have to build these, but I wanted you to build it first. Okay. Chiral. Many molecules have two chiral forms. Once you get the models out, all the heck breaks those. Okay. Also, in biological systems, an enzyme will use one form of molecule, chiral molecule, but not the other. So why is it important? Further study biology and biochemistry, then it becomes quite important. So, to do the last question, I'd say the easiest way to draw the optical isomers to draw the mirror image is very clear. There's other ways of drawing it. But if it has a chiral center, how many different attachments do you have to the carbon? 4. So first of all, it must have 4. So let's just do elimination, say which one's a no. So A is a yes. I'm going to just put a yes here, though. B is a no because it's, yeah, that hydrogen is no. Okay. C is a no because it only has. Which of the following have a chiral center? First, so. A chiral center is where you have 4. This is a chiral center here. 4 different attacks. And D is a yes. Because it has 4 different attacks. Okay? So, to do the mirror image then is the quickest way to draw the optical isomer. So I'm going to just do that in red here. So I think of this, I'm just drawing this like a mirror. Put away your stuff, we will continue this tomorrow.